BLAST stands for the Balloon-borne Large Aperture Submillimeter Telescope, and it's called that because it's a balloon-borne large aperture submillimeter telescope. So pretty much the name describes what it does. So our galaxy forms about 4 stars per year, and we were measuring that you should probably get more like 70 or 80 stars per year. So, and this has been known for some time, this is a problem. So we're looking for that. We're just basically going to survey a dozen clouds from Antarctica, looking into our galaxy, and try to determine the statistics of what's going on inside the clouds.
I always knew when I was applying to grad schools that I wanted to make things going into space. The balloon projects are really neat because I think more than any other sort of astrophysics hardware, telescope hardware, the students and the people here get to make a lot more. I mean, we've touched everything that's on this experiment, right? We've developed it, we've designed it, we put it all together.
We use high-altitude ballooning in astronomy essentially as a four-person satellite. A satellite costs $1 billion or more. A balloon launch traditionally costs quite a bit less. So when you launch a balloon, you go above most of the atmosphere, about 99.5% of the atmosphere is below you, and you can get a very clear view of what's going on. At our waveband, which is in the sub-millimeter waveband, the atmosphere here at sea level is essentially opaque. In other words, you can't see anything. So if I were to look up with our telescope here, we would just see black, and there'd be nothing to see. So you have to get above most of the atmosphere in order to have the sensitivity to do it.
The nice thing about came here and start to work on BLAST has allowed me to broaden my astrophysics knowledge from a pure cosmic microwave background and cosmology background to a star formation and our galaxy knowledge. You want to be like flexible in the future if you want to be a scientist.
You know, I think the best part of working on this has been just all of the breakthroughs that we had in Texas. We went to Texas with an experiment that we were pretty sure was going to work, but there were still a lot of hurdles that we needed to get over. The whole team was there from all of the different institutions for a month and a half or so, and we just slowly crossed everything off the list. We fixed helium leaks, we fixed readout system, we put everything together for the first time. The mirror just went on smoothly. One after another, everything started to work.
You know, when we first flew BLAST in 2006, nobody had ever seen these things, right? Nobody ever seen it. And so what we did then was to just increase the knowledge base by several orders of magnitude in what was going on. Part of my other work is studying the origins of the universe itself. You know, where did the galaxies come from? How did they form? But more locally, you want to say, well, you know, here's our star. How did they get there? And why aren't there more stars? Why aren't there stars closer to us? Why, what is basically governing how things happen in our galaxy? So as a general interest thing, it's nice to know. It's not going to change anybody's everyday life on whether or not we understand how stars form in our galaxy. But what astronomers and cosmologists and astrophysicists are trying to do is kind of fill in the picture, to have a complete understanding of what's happening in the universe. And this is one part of that.